Please don't forget to like, subscribe, and comment. Thank you so much.
Join us at Like Learning School and experience a transformative education journey. Visit our website at www.likelearningschool.com or contact us at +2348085095144 to learn more and get started today.
Alright, these are applications of force on a current or on a current carrying conductor inside a magnetic field, or what we call generally as motor effect. The question says, when the switch is closed, the copper wire moves. Well, this is just an additional information because one of the ways you can be asked to describe this is, what will happen to the copper wire when the switch is closed? This is the copper wire here. And then it says, describe how the direction that the copper wire move can be predicted using Fleming's left-hand rule. First of all, anytime you are doing this, like I've always told you, you need to get the direction of the conventional current. You know, conventional current direction is from positive to negative. So you start from the positive side of the battery, walk round. That's the red line I showed you, just for additional information to help you predict this. Once you close this switch, current will flow from the positive side of the battery through these copper rails and then enters through the copper wire, resting with rails, and then flow into the other rail, back to the wire and to the negative side of the battery. And the cycle continues. You get what I'm saying? Now you should first of all think about what happens here. What happens here, and like you see, as you can see, current is flowing out of the paper, isn't it? It's flowing out of the paper. If it is flowing out of the paper like this, flowing like jumping out of the screen, jumping out of the paper. It is jumping out of the paper by Fleming's left-hand rule. Your thumb will point to the left, isn't it? Because this is the knot. I hope you all figured it out. Dennis, can you put your hand to demonstrate this? Now the simple thing to do is start with your, this is basically the rule you are using. This. In fact, this gives it exactly. This particular diagram gives it exactly. Current is jumping out of the board, is it not? Which one represents the current? The second finger. The second finger represents the direction of the conventional current. And how is it flowing this time around? It's jumping out of the board, is it not? Out of the paper. For you, you will say out of paper. How is the magnetic field? From bottom to top. From bottom to top. Which side will the force or push is to the left? That's exactly what happened there. Look at it. That's exactly what happened there. Where the copper wire is, look at how the current is coming out of the board, is it not? It's coming out of the screen, out of the laptop screen, out of your paper. And then that's how the current is jumping out of the screen. Then you need to also look at how the magnetic field is from bottom to top. From bottom to top. Bottom here, top here. So your first finger should point upward, like the diagram I showed you. Then your thumb will show you the direction of the push, which of course is to the left. So this copper wire will move to the left, isn't it? Like we showed here. Alright, in describing it, how will you describe it fully, like I explained to you earlier? How will you describe it fully? The wire will move. The wire will move to the left.
At 90 degrees.
At 90 degrees.
To the magnetic field.
To the magnetic field. Or conventional current. According to Fleming's left-hand rule. Beautiful. So because this is what we show how the direction of the wire. The copper wire will move to the left at right angles to Fleming's at right angles to magnetic field or conventional current according to Fleming's left-hand rule. So the simple rule is this: if your first finger points in the direction of what? If your first finger points in the direction of what? No, if your first finger points in the direction of what? Magnetic field, and your second finger points in the direction of conventional current, your thumb will point in the direction of the force, the thrust. So long as all of them are at right angles to each other, like this. You can see this is 90 degrees to this, isn't it? This is 90 degrees to this, and this one is also 90 degrees to this. All of them, first finger and second finger at 90 degrees to each other. Second finger and thumb at 90 degrees to each other. First finger and thumb at 90 degrees to each other. That's Fleming's left-hand rule. We use Fleming's left-hand rule to predict the direction of the force, the push. Did you get that? For motor effect. Usually we know the direction of the magnetic field. Like this time it is pointing from bottom to top. And we also know the direction of conventional current. Like this one, it is jumping out of the paper. This finger jumping out of the paper. Then we can predict the direction of the push, which will be to the left. Is that clear? Fleming's left-hand rule is to show us the direction of the push. Now that's what we call motor effect. Whenever a charge flows through a conductor or a conducting medium that is inside an already existing magnetic field, the conductor or that moving charge will experience a force. And the direction of the force is predicted by Fleming's left-hand rule. Just to summarize what we have said, that anytime current flows through a conductor, like this current is flowing through a conductor, and this conductor finds itself inside a magnetic field, because this magnetic field is already provided by the permanent magnet having north and south, isn't it? There will be a force or a push on that conductor, or a push on that moving charge, which is current, and the direction of that push is predicted using Fleming's left-hand rule. Why is that push? Don't remind me again. Why do we have that push? What is responsible for that push? What is responsible for that push? Can you explain? Can you remind me again? We talked about it earlier in the previous discussion. What is responsible for that push?
Interaction of the two magnetic fields.
Good. The interaction of the two magnetic fields. One from the permanent magnet. Incidentally, I decided to represent it in blue. You see, this is a north pole of a permanent magnet. This is a south pole of the permanent magnet. Magnetic lines of forces run from north to. That's what I represented in blue. There's a magnetic field in blue from the permanent magnet, and then the other from the electromagnet. Is it not? And how does an electromagnet form? What forms an electromagnet? Whenever current flows through a conductor, isn't it? So once you have a moving charge, there's a magnetic field around it. Once current flows through a conductor, a magnetic field forms around it. And that's what we call an electromagnet, isn't it? Or an electromagnetic field. What's the shape of the magnetic field for a straight conductor? Circular, right? Concentric circles. And you can predict the direction of that using right-hand grip rule. Right-hand grip rule. We talked about all that earlier. Right-hand grip rule. Okay. Motor effect. Motor effect is about a push on a moving charge or a current that is carrying a conductor that is carrying a current, because that conductor is inside a magnetic field. And I want to show you how this finds application in simple devices. Look at this. I think I can zoom out a bit to reveal this better. Okay, it's revealing it properly. watch this. This is a horseshoe magnet. Horseshoe is just one piece of magnet that you can curve to provide a space through which you can pass the coil or solenoid. Unlike having one magnet with a north pole and another one with a south pole, we can have one particular magnet that we just coil that will bend in form of a shape of a U. You understand what I mean? So this is the north pole of this magnet, this is the south pole of this magnet. Okay? Are you listening? Now let's go. Can you see the positive side of the battery? Where is the positive of the battery? The longer side, am I right? That's the positive side. Let me represent it very well. Plus. Then the negative side is this one. Am I right? Okay. Of course, I always tell you need to first of all identify the conventional current direction, isn't it? Conventional current direction from positive to. So this current flows out of the battery or the cell, enters into what we call carbon brushes. And then from the carbon brush, it enters into a commutator or a split ring. Just a ring split into two. You know a ring, wedding ring and all of that, cut into two halves. One part and the other part. We call that a commutator. What's another name for a split ring? A commutator is a split ring. There's a reason for that. I will explain now. First of all, the current, I'm just showing the direction of the conventional current. But you know electrons actually flow the other way around. I hope you know. Convention is just the traditional way it was understood. So current flows through here from the positive side of the cell into the carbon brush, and then from the carbon brush it enters into what? The commutator. From the commutator a wire runs through a solenoid, coils, and then back to the other side of the commutator. From this other side of the commutator it flows into the carbon brush and back to the other side of the negative side of the cell. Stay alert. I want us to confirm these directions I showed earlier. I could have erased them, but let's just confirm them. Let's confirm if this wire on this side will actually be pushed down, while the wire on this other side will be pushed up. Let's confirm. Where is the north pole? The south pole? Okay, so show it. North pole this way. South pole.
No, South Pole.
That's north pole here. Where's the north pole? The north pole is on the left now, is it not? The north pole is on the left. The south pole is on the right. So it's going this way, is it not? The magnetic field is flowing towards where? The right. Have you represented that? Good. 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 You are doing right. You are doing well. Now watch this. What does the second finger represent? Conventional current. How is, in the way you are representing it, this second finger is pointing where? Out of the paper, right? Out of the paper. Based on your representation, the second finger is pointing out of the paper. What? Now you see the side that is flowing out of the paper. Watch me. You can see what color can I use? Let me use this yellow line. This one is flowing out of the paper, isn't it? Can you see this current here is flowing out of the paper? Whereas this side it is flowing what? Do you know that? Because the current flows like this into the carbon brush, to the commutator, to the solenoid. This side of the solenoid is flowing into the paper, is it not? It's flowing into the paper this side. On the side of the solenoid, this side of the solenoid is flowing into the paper. Whereas this side of the solenoid is flowing this side that is flowing out of the paper. Use your this to confirm if the force will push it up. Has it been confirmed? The force is definitely going to push it up, isn't it? Is it confirmed? So this side of the coil will be pushed up based on Fleming's left hand rule. Obviously, If it is flowing out of the paper and it is pushed up, without even bothering yourself, when it's flowing into the paper, it must be pushed down, based on what I told you. Once you reverse the current, the force will also be reversed. Did you get that? So I said, on this side of the paper, on this side of the coil, where the current is flowing out of the paper or out of the screen, jumping to you, the wire will be pushed what? Up. As you can see, this white arrow. On this side of the paper, on this side of the coil, where the current is flowing into the paper without even bothering yourself, you know it will be pushed down, is it not? So what do you think will happen? There's a force pushing up on one side and pushing down on the other side. So what do you think will happen? If this, look at this book, if this side is pushed up and this side is pushed down, this side is pushed up, this side is pushed down, what do you think will happen? It will be a continuous rotation. That is the principal operation of all electric motors. This is your electric fan, that's how it works. All you need is for current, watch me, for current to flow through a wire, a solenoid that finds itself inside a magnetic field. One side of the solenoid will be pushed up, the other side will be pushed down, and then to maintain a continuous rotation, you need this carbon brush, this commutator. How does it work? See, when this side is pushed down, are you listening to me? When this side is pushed down, you know, it goes down and carries the carbon brush with it. As it is rotating, it takes this carbon brush to the other side, is it not? While this side that is pushed up, as it is rotating, it carries the other carbon brush to this side. So there will be a continuous rotation, because in all the times the circuit is not disconnected, current is not cut off. I want to help you to see that again. This is where I talked about what the commutator does. The function of the commutator, let me just read it out, then I will talk about it. What's the function of the commutator? Which of course we call split ring. Let's read it out. The function of the commutator or split ring is to reverse the current direction in the rotating windings each half turn, so as to maintain a steady rotation or rotating force or torque. If you remember your moment is force and distance, isn't it? But let me not get deeper. At A levels we talk about torque, which is moment of a force, a moment of a couple. They don't bother about it now. But this is a couple. Sometimes you may need to even add that in your explanation. This is a couple. A couple is a pair of equal, opposite, parallel forces acting at a distance between each other. Equal, opposite, and there's usually three characteristics. They must be equal, they must be opposite, and they must have the same size. For instance, if this one is 20 Newton, it's acting upward, is it not? This one also 20 Newton. They are equal and opposite, isn't it? Acting in opposite directions. One acts upward, the other one acts downward, separated by a distance. Once they keep acting, it will produce a rotation. That's what we call couple. A couple is a pair of equal, opposite, and parallel forces acting to produce a rotation. So this couple will produce a rotation, but to make sure that that rotation is sustained, because when you put on this your fan, it needs to keep rotating. When you put it on, what happens? It stops rotating. As long as current is flowing, it must continue to rotate. So how do we make sure that current continues to flow? using this commutator, because as this one is going down, as I explained to you, this commutator is fixed to this wire. I hope you know. It carries, you see, just like, think about it, when this drags down, you know, it carries this commutator down until it switches it to this other side. And this one is now going up. It also carries this commutator up and switches it to this other side. Can you visualize what I'm trying to say? It's rotating because when this is going, this side of the solenoid is going down, it carries this commutator with it because it's a rotation. It will carry it and take it to this other side, to the left hand side. While the one on the right hand side, because it is going up, will be carried to the right hand side. And because they are long enough, let me just show you something. This is long enough. As soon as this one is completing its motion into this other side, this one has already entered. So in all cases, current is continuously flowing. There's no time that current doesn't flow, because once current stops flowing, the rotation stops. The commutator helps to maintain rotation. That's what I want to explain to you. Are we good on that? This is an electric motor. What is the energy transformation in this electric motor? Can you tell me? From what?
To kinetic.
Yes, what energy entered? Electrical energy. What did it produce?
Kinetic.
How did you know it produced kinetic?
Good, how? It's
Because it's
producing.
turning.
Because it's turning. Yeah, that's correct. Current flowed into this, and because that current finds itself in the magnetic field, there's a push on the wire which is carrying the current, and that push is kinetic, is it not? It moves. So the energy transformation in an electric motor is from the energy transformation in an electric motor. The energy transformation in an electric motor is from electrical to kinetic. Electrical is the energy input, kinetic is the energy output. And I said the commutator helps to make sure that we maintain constant contact with the current. As this goes down, because it's a rotation, it carries this commutator to the left hand side, while the commutator on the right hand side, it is carried to the left hand side. And if you see the way it is, as soon as this one is coming into here, once this one is trying to make contact with this, or has made contact with this one has already made contact with this one. So there's no time this circuit is broken. In all cases, the circuit is closed. Current can continuously flow, Sometimes these things are drawn and you're asked to level. What did I call this place? What did I call this one? Carbon brushes, or brushes made of carbon. What did I call these split rings? Okay, to maintain rotation. Okay. You see, this motor effect can also find application in all moving coil meters, like your galvanometer, ammeter, voltmeter, with a coil. Something like this can help to illustrate it. Let me see this question very quickly. Look at this question. Are you ready? Let me show you. When you close this switch, what happens? Current flows, is it not? You should always represent the direction of the current. It flows like this into here, am I right? Into here, back here again, and continues. So it flows from positive to here, to here, to here, and back. I should have told you something. Okay, just take note of this before we talk about that. How will this thing move? Can we use our Fleming's left hand rule to predict? Can we? Let's see. Are you getting what I'm saying? Imagine I supply the current of 5 amps. this pointer will move based on how much this current of 5 amps moved it to the left, is it not? Now if I increase this current to 10 amps, what do you think will happen to them? What can you say about how far the pointer will move? It will move much more farther. That's for 5 amps flowing. Now when you now have 10 amps flowing, you know, more current means what? More push. So will it push it beyond or less? If you push, this pointer will push it beyond. So this pointer will move beyond the original position B. It will move even beyond B. Perhaps it might even move up to C. So we have used this to measure this current. More current, more shifts. More current, more shifts. That's a meter, like an ammeter or a voltmeter. When you were reading those moving coil instruments, you notice that when you plot, when you carry out your Ohm's law experiment, you saw that if you had something more, then it deflects much more. That's the principle of operation of all moving coil meters. That's the way it operates. All it does is, with a greater current, the pointer moves further, and then we use how far the pointer has moved to measure the amount of the current, or even the amount of the voltage. So moving coil meters like an ammeter, a voltmeter, a galvanometer, all works on this principle. Motor effect. When current flows of a particular value, it experiences a push. This push from a pointer at 0 position, we move from this 0 to a new position. This point is very important. I think I have to just emphasize this. Read it out. No force is experienced when the current is parallel to the direction of the magnetic field. Let me say that again. No force is experienced when the current is parallel to the direction of the magnetic field. Which line shows a current parallel? Like something like C to D is in the same axis with the magnetic field. The magnetic field is going from where? Just tell me from left to right, is it not? Left to right. And the alignment of C to D is also from left to right. There's no force along C to D. Why? Because it is parallel to the direction of magnetic field. There's a force between E to D. Why? It's perpendicular to the magnetic field. In summary, even when current is flowing through a piece of wire, if that conductor or wire is parallel to the magnetic field, it experiences no force. Did you hear me? In fact, if though it's beyond your scope, the value of that force is usually, you can get it by using this formula BI sine theta, or cos theta rather. Please don't forget to like, subscribe, and comment. Thank you so much.
Welcome to Like Learning School, your premier online education platform. At Like Learning School, we are dedicated to helping students and learners unlock their full potential, providing them with the foundation, support, and guidance they need for academic excellence. Our platform caters to two main target audiences. Firstly, we work with school children of all ages, offering academic follow-up and accountability partnerships. Our seasoned tutors provide personalized attention to ensure students stay on track and reach their goals. Secondly, we support students and learners who are preparing for internal, external, entrance, or professional examinations. We offer comprehensive and well-structured support to help them achieve outstanding performance in their exams. Our robust virtual courses are designed to keep students engaged and motivated. With interactive videos showcasing our teaching sessions, students actively participate in the learning process, making education enjoyable and effective. But that's not all. We believe in personalized education. Our students have access to personalized tutorial sessions, whether online, physical, or hybrid, tailored to their unique learning needs. Join us at Like Learning School and experience a transformative education journey. Visit our website at www.likelearningschool.com or contact us at +234 808 509 5144 to learn more and get started today.